Hey, we're going to start talking about integration by parts, which is one of our big integration techniques that we will need moving forward. And what integration by parts is used for is when you want to integrate the product of two seemingly unrelated functions. So my first example down here, before I give you the formula, I've got the integral of 2x times the sine of x. And at first that looks like possibly a u substitution, but if you try it and you let u equal, say, sine of x, du equals cosine of x, the pairing is not there. It doesn't work that way, and even if you just let u be the x here, the derivative is just 1. So you don't have a way of getting rid of this part on the outside. You can change it to both u's, but it doesn't really help. So in this case right here, what we see is we've got two things multiplied together, the 2x and the sine x, and we're trying to figure out how we can turn that around into an integration. Well, the thing to remember is, where do products of weird things come from? And they will come from basically the product rule. So what I've got here is the product rule as we know it. Derivative of u times v is u times v prime, which I'm calling dv, plus v times u prime, which I'm calling du. So in that case, if we write out the product rule, derivative u times v equals its derivative on the right hand side, we know that if we want to turn something around, we can take the antiderivative, and we could basically reverse this whole process. So we can take the antiderivative of both sides of that product rule. Now on the left hand side, where I've got the integral of the derivative, that just cancels out. So if you think about what we've got there, this integral and this derivative knock itself out and just leave the u times v. Now on the right hand side, I've got the integral of this sum, and through a sum difference rule of integration, we can take the integral of those two things separately. So in this case, you see u times v equals the integral of u dv plus integral of v du. So what we're going to do is we're going to kind of isolate one of these, and what we choose to isolate in this case is the u dv integral. So we'll put that on one side, and what we did was we moved this other integral to the other side. So the integral of u dv, which, remember, these are two functions. Basically u is an expression or a function, and dv or v prime is another function or expression that's the derivative of something. So if we have u and dv, there's possibly a way to figure out from integrating dv or v prime to get v, and there's a way from having u to get du or u prime. So that integration by parts formula that we're going to use, at least for right now, is the integral of u dv equals u times v minus the integral of v du. So we just took the product rule, reversed it, and kind of isolated one part. So let's try and see this in action here. So let's kind of skip down to my example here, where we're going to have the integral of what I had, 2x, and then times the sine of x dx. And I write this way because what we're going to do is we're going to label them. The 2x will be the u, and the sine x dx will be the dv. So we have to have something that we can take the derivative of, and we have to have something we can integrate. Okay, so all my u parts up here kind of stick out, and all my v parts kind of stick out as well. So if u is 2x, then the derivative of u is 2 dx, if we're talking about a u substitution in a way. And if dv is the sine of x, I'm going to integrate that to get v. So integral of sine is negative cosine. So I can come back into my formula and drop everything in. So the formula says that the integral of u times dv, don't know why that disappeared, equals u times the integral of dv, so that's the v, minus the integral of, in this case, v, which is the negative cosine times the du, which is 2x. So let's label all that stuff. So here is u, du, and that's v, not dv. Mr. Eraser, you're our friend today. U times v minus v du integral. Okay, so what that does when I clean it up, I've got my integral that I'm trying to find is equal to, in this case, negative 2x cosine of x, and then I have still another integral, which the two negatives cancel out, so plus the integral of 2 cosine dx, which in this case I can integrate this without using this integration by parts or another technique, because the 2 will just sit there as a coefficient, and I can integrate the cosine with a formula. So the integral of cosine is sine. So in the end, it took us a little bit of work, but we got the integral of 2x sine x to be negative 2x cosine plus 2 sine. And of course, there's a plus c since that's a indefinite integral. Okay, so we just got to identify these parts and use them appropriately. Let's see if we got another example here. So this is a longer example. Maybe not as much fun, but it says the integral of x squared equals e to the x dx. So once again, you might think you could use a u substitution here, but in this case, if you let u be x, the du is going to be just 1, which doesn't really correspond to what's in front here. So if we look at this thing and try and break it apart, we can see that we have a u and a dv. Okay, and I've let those be listed down here. Okay, in that case, if u is x squared, then du will be 2x. And then if dv is e to the x, the integral of e to the x is just e to the x. So when I drop all those things in, let me see, we want to color code everything. So if we do that, we drop everything in, we will have u v minus the integral of v, which is right here, du. Du is great. Now, unfortunately, what happens here when we set all this up is that we still have something that we don't have an integration rule for. So x squared times e to the x, the u times v is integrated, so we're done with that part. But the minus integral of 2x e to the x dx, really what we're going to have to do is we're going to have to use this integration by parts again. So in that case, we'll go through the whole thing with the 2x e to the x, let u be 2x, and then the derivative of that be 2. And let dv be e to the x, and the integral of that is e to the x. So we have the part that was already up top, the x squared e to the x that we got out of the first iteration of doing this, and then we've got the part that we are trying to work with. Okay, now the integration of the second part. So with that in mind, we come through this again, and we've got a big old negative sign out here because we're subtracting this whole integral. The integral does give us something nice, and then it gives us another integral. Distribute that negative sign, but we get, again, something else we got to integrate in the end. So from bringing from the first time I tried this, I got x squared times e to the x. From the second integration by parts, I've got minus 2x e to the x. Plus, and I've still got this integral of 2e to the x to handle. But the integral of 2e to the x is, well, 2e to the x. So everything works out. I can complete this eventually. Alright, I think we will stop right there. But something that's useful here to know is that you have to be able to take the derivative of it, and that dv, you have to be able to integrate it. So it could be switched around a little bit. In this case, so both of these x squared and e to the x, you can do both things with. but what you find in this case, letting the x squared be the u is really the helpful thing, because if you do this process enough, x squared will go to 0 eventually if you keep taking a derivative over and over. Alright, let's stop there for now.